When we look at applications of linear systems graphically, we first need to understand how to interpret those linear system graphs. So we're going to take a look at some examples. So in each of these graphs, we're going to compare the rental costs for the two halls. We're going to describe what the point of intersection represents, and then we're going to take that further and talk about when will each hall be cheaper. So the first thing that we want to do is we want to identify the point of intersection. So the point of intersection for this first graph is right here at the coordinate 150, 4,500. So what does that mean? Well, that means when the hall, or when you have 150 guests, then the cost of each hall will be exactly the same. So if you're inviting exactly 150 guests, and it doesn't matter whether you rent hall C or hall D in this case. But sometimes you're not going to have exactly the right amount of guests to make both of those scenarios going to be equal. So sometimes we might have less than 150 guests, and sometimes we might have more than 150 guests. And so what will that look like in terms of making your decision about which hall to rent? So for part B of this question, or I guess it was part 1 and part 2, but it doesn't really matter. So part 1 and part 2. So part 2 says how many guests is each hall cheaper? So if we look at this, and if the number of guests is less than 150 people, so remember the less than or greater than symbols. So if the number of guests is less than 150, then if we look at our graph, the line that's lower is hall C. So hall C will be cheaper. But if the number of guests is greater than 150, then again, after this point, we need to look at which line is lower, and the blue line is lower than the red line, and that represents hall D. So hall D will be cheaper. So when we're looking at systems of linear equations and we're looking at the applications of them, the point of intersection will tell us when both of those situations will be the same, and then either before or after that will determine information about one scenario versus the other, being either better or worse than the other one. So now let's take a look at the second example. So again, we need to find our point of intersection. So the point of intersection is right here at the point that has a coordinate 240 and then 18,000. So what does that mean? Well, that means that when you have 240 guests, the cost for each hall will be $18,000. And when will it be cheaper? Well, if you have less than 240 people, then again, we look at our graph, which line is below. That's the purple line, which represents hall E. So hall E is cheaper. But if you are inviting more than 240 people, then we look at what happens after that point of intersection, and the green line is lower, and the green line represents hall F. So when we're first looking at how to interpret equations of linear systems, sometimes it's helpful, again, to see what it looks like graphically, because then we can see clearly when one situation is going to be better than the other. Let's take a look at another example. So here we have an example where we are looking at the cost to produce pizzas versus the cost to sell pizzas. So if you are looking at working at a pizza shop, for example, you're going to have a cost to make those pizzas. So the cost of all of the ingredients, the cost to pay your employees, and so on. And those costs to produce the pizza is going to be different, and hopefully it'll be less than what you charge people to buy that pizza. Because ideally you want to be able to make a profit so you can keep your business going. So in this example, we have the cost of pizzas is the title of our graph, where we have cost and income along the side. So this is the amount of money that we're either losing because we are purchasing ingredients to sell pizza, or income that we're getting because that's what we're getting when we sell the pizza. And the bottom represents the number of pizzas being sold or being made. Okay, so graph A, so the red line, represents the daily cost to produce the pizza. So for each number of pizzas that you make throughout the day, this is how much it would cost to make those pizzas. The blue line represents how much you're going to earn by selling the pizzas. So we'll notice that if you don't sell any pizza, you make $0. If we look at how much the cost, so the original cost to make pizzas was $200. So this might be the cost to employ your employees, right? Or the equipment, or the rent, or heat, hydro, all those things, right? In order to run a business. So what does that point of intersection represent? So we have a point of intersection right here at the coordinate 30 and 350. So what does that mean? Well, that point of intersection means that if you make or sell 30 pizzas, the cost and the income will be $350. So what we call that is the break-even point. So that's where the amount of cost will equal the amount of income that you're getting. So if you sell 30 pizzas, you don't make or lose any money. So the amount that you get equals the amount that you pay out. So how many pizzas must be sold before there's a profit? So that means that the income is greater than the cost. So remember, the red line represents the cost and the blue line represents the income. So when is the blue line above the red line? That occurs after our point of intersection. So that means any number of pizzas we sell after 30 will mean that we have a profit in our bank. So for part B, so if you sell more than 30 pizzas, you will make a profit. And the amount of profit will increase for the more pizzas that you sell. So once we know how to interpret that point of intersection, now it's time to take this a step further. So now it's time to understand how we can model word problems using linear systems. So when you see the word model, when we're asked to model a word problem using a system of linear equations, what we need to do is we need to define our variables using let statements. So sometimes you're not going to get equations provided to you in a word problem. Sometimes you're going to have to make up your own equations. So before we can make up our equations, we have to identify what those variables are going to be. So what is our x going to be? What is our y going to be? And we don't always have to use x and y. Sometimes we can use the letters that will make sense in terms of our problem. So once we've defined the variables, now we can create each of our equations. So model just means to set up in mathematical form the equations of our situation. So there are two types of linear system problems that we're going to encounter. The first is when we have a single scenario under different conditions. So this might be one problem, and we're looking at two different people in terms of that problem. So we're looking at trying to come up with one scenario under different conditions. And we're not going to solve any of these. We're just going to take a look at identifying variables and coming up with equations for each of these at this point, just so we have some of that practice. So for example, this example says that Jason weighs 6 kilograms less than twice Bill's weight. If the sum of their weights is 102 kilograms, how much does each person weigh? Well, we have two people. We have Jason and we have Bill. And so those are the people that we are going to have to determine the weight for, because it says how much does each person weigh. So I'm looking to find how much Jason weighs, and I want to find a numerical value for how much Bill weighs. So I might say, let J represent Jason's weight. And I might let B represent Bill's weight. I could have used X and Y, but if I use J and B, then when we start to look at solving for those variables, then it's easier for us to remember which one was what. So now that I've identified the variables that I'm going to use in my equation, I'm going to come up with an equation for each of these sentences. So I want to come up with an equation to represent this statement right here. So Jason's weight is 6 kilograms less than twice a Bill's weight. So that's the first equation that I'm going to come up with. So I want to make an equation so that Jason is equal to twice of Bill's, so 2 times Bill's, but 6 kilograms less than that. So twice of Bill's weight, subtract 6 kilograms will be what Jason weighs. So twice of Bill's weight, less than. So less than means you're subtracting it from. So less than means subtraction. So I'm subtracting 6 kilograms from twice of Bill's weight, and that's going to give me Jason's weight. Now I'm going to come up with an equation for the second sentence. So if the sum of their weights is 102 kilograms, so that's the next equation that I need to come up with. So I know that the sum is addition. So Jason plus Bill will equal 102 kilograms. So J plus B is equal to 102 kilograms. So those are the two equations that I'm going to use for this problem. I don't want to solve it at this point, so I just wanted to make sure that I know how to represent the variables and how I can come up with an equation. So that's one example where you have a single scenario under different conditions. The second type of problem you might have is where you have different scenarios. So this is when we're comparing two different companies, for example. So we have different scenarios under the same condition. So this is what this might look like. Carl's towing charges $80 plus 22 cents per kilometer. Bev's towing charges $70 plus 30 cents per kilometer. We want to write a linear system to represent this problem. So we have to come up with two different equations, and we're going to use those equations to figure out which towing company would we use. And we would make that decision based on what happens before the point of intersection and what happens after that point of intersection. So first of all, I need to come up with some variables. So I want to know my total cost. So I might say, let C represent the total cost. And I might let K represent the number of kilometers. Because the cost is determined by how many kilometers that I'm being towed by. And I'm going to come up with an equation for both Carl and for both Bev. So here's Carl's equation. So for Carl, I'm using this information to come up with an equation. So the total cost, if I go with Carl's towing, would be $80. So he's going to charge me $80 no matter what. And then he's charging me 22 cents per kilometer. So every kilometer I get towed, I'm being charged 22 cents. So this number will change based on the number of kilometers that I get towed. So that's Carl's total cost. Now I want to see how much it's going to cost if I use Bev's towing company. So what will that cost be? Well, let's take a look at the information for Bev. So Bev's charges $70 plus 30 cents per kilometer. So let's use that information to come up with the equation. So the total cost is $70. So I get charged $70 no matter what, plus 30 cents per kilometer. Okay, so those are the two equations that I would use for this problem here. I could graph these on a set of Cartesian plane or a set of axes, and I could then determine which one will be better for me depending on how far I need to be towed. So let's just practice coming up with some equations, because that can be the trickiest part when we're looking at applications of linear systems. So can you come up with the correct equations? So we're not going to solve anything for this one. We're just going to come up with the equations to make this problem be something that we could solve. So remember, when we're coming up with equations, we also have to define our variables. So what do the variables stand for? What do the letters stand for in our problem? So this example, Jill makes two types of quilts. The first type costs $25 for fabric and $40 per hour for hand quilting. The second type costs $50 for fabric and $22 per hour for machine quilting. So whether I'm doing it by a sewing machine or by hand will determine the difference in the cost per hour. And I want to know for what number of hours are the costs the same. So I have to determine the total cost. So that's going to be one of my variables. So I'm going to say, let C represent the total cost. And what determines the total cost? That's the number of hours. So I'm going to let H represent the number of hours. And now we have two different types of quilting that we can do. We can have hand quilting, that's type 1, and we can have machine quilting, that's type 2. So I have to come up with two equations based on these scenarios. So let's take a look at the formula for hand quilting. So the first type costs $25 for fabric and $40 per hour for hand quilting. So that's my first one. So hand quilting costs $25. So the C, the total cost, is $25 for the fabric plus $40 per hour. Anytime you see that per kilometer, per hour, per person, that's going to be the number times the variable. Okay, so that's a hint for that as well. And then the just number all by itself would be your like B value, so your y-intercept, or your initial value is sometimes what it's called. We also have to come up with an equation for the machine sewing or the machine quilting. So again, let's take a look at that information. So the second type costs $50 for fabric and $22 per hour for machine quilting. So that's the information I'm going to use for this problem. So the total cost is $50 for the fabric plus $22 per hour. So $22 times my H. So this will determine my total cost. So the fabric cost will be the same, and then the hourly wage goes up depending on how long you have to do the quilting for. So those would be the two equations for this situation. Let's take a look at the next example. A band held a concert in its hometown. A total of 15,000 people attended. The tickets cost $8 for students and $12.50 for adults. The concert took in a total of $162,500. How many adults came to the concert? Well, we need to know two things. We need to know how many students come and how many adults come, because those are the two different situations. So students and adults. So those are going to be our variables. So we can say let S represent the number of students and let A represent the number of adults. So this would be an example of a single scenario, and we have different conditions that are going to be happening in order for us to make our equations. So our first equation we're going to take a look at. We're going to come up with an equation to represent the total number of people. So it says a total of 15,000 people attended. Well, those people consisted of both adults and students. So for this equation, we would have the number of students plus the number of adults is equal to 15,000. Okay. Now we have to come up with an equation that represents the total cost. So it says the tickets cost $8 per student and $12 per adult, and they make a total of $162,500. So I'm going to come up with an equation that represents the cost now. I have equation for the number of people. Now I need an equation for the total cost. So I make $8 per student. So remember that per means multiplication. So $8 times S plus I make $12.50 per adult, so times A, and that total amount that I'm making is $162,500. So those are the two equations that I would come up with. So now that we've spent some time looking at how we can come up with an equation, and we looked at how to interpret the results based on a graph, let's put those two pieces together and work on a couple more examples. So this first example includes renting a video game machine and video games. So back in the day when I was a kid, I had to not only rent, could rent videos, so like movies to watch. Think Blockbuster. If you've ever seen, there's a documentary about Blockbuster. You might have heard of it before. Ask your parents, they'll know. So, and then you could also sometimes rent a game machine, like back in the day it was a Super Nintendo, and then you could also rent the video games that go along with that. So Galaxy Video rents a game machine for $10. So it costs $10 to rent that video game machine. And then each game that you want to play on that machine is $3 to rent. For Less Video rents a game machine for only $7, but their video games are $4 each. So we want to come up with an equation for each of these two companies to represent the cost of renting one game machine and the video games at each store. So first of all, we need to define our variables. Well, we know that we're going to have to figure out the cost. So that's going to be one of our variables. So let C represent the total cost. Again, you could use X and Y if you want to, but just go ahead and use the letter that corresponds to what you're trying to find. That makes it easier in the long run. So let C represent the total cost. And some people like to put that it's represented in dollars, especially if you're dealing with currency from another country, but we're going to assume it's dollars for us. And we also have to know that how many video games we're renting. So that's going to be the other variable that we have. So let's call it G. So let G represent the number of games, because that's going to change our cost. So the game console costs us one's fixed rate, and then how many video games we rent will determine our total cost. So now let's come up with some equations. We're going to come up with an equation for Galaxy Video. So that's G. I'm going to make it that G. So here. So for Galaxy, our total cost is $10 plus $3 for each game. Now I'm going to come up with an equation for Less Video. So the total cost is $7 for the game console and $4 for each game. So those are the two equations that I'm going to use. And I'm using different colors so that when I graph it, I can clearly see which one is which. So the first thing I want to do is create a table of values for each of these equations. And when I create this table of values, it says use a maximum number of 6 video games. Okay, so let's take a look at this information. So I'm going to create a table of values for Galaxy. I'm going to use my green to represent Galaxy. I'm going to stay consistent with my colors. So I'm going to have the number of games in one column, because that's going to change, and my total cost in the second one, because cost is dependent on the number of games that I rent. If I just rent the console, so let's say I have games already at home, but my Super Nintendo broke, then it just costs me $10 to rent that video game machine. If I rent one game, it's going to cost me $10 plus $3, which is $13. If I rent 2 games, I add another $3 to that, which is $16. I can keep going. $3 would be $19. I'm going to continue my chart over here. 4 games, I'm going to add another $3 to this to $22. 5 games would be $25. And 6 games would be $28. So after I have my initial amount, I'm adding another $3 for each of those games. Now I'm going to come up with a table of values for Less Video. So again, I'm going to look at the number of games I rent versus the total cost. So if I don't rent any games and I just rent the video game machine, it's going to cost me $7. If I also rent one game, I add $4 to that. So 7 plus 4 is 11. If I make 2 games or rent 2 games, it's 11 plus 4, which is 15. If I rent 3 games, I'm adding another $4 to that to give me 19. I'm going to continue my chart over here. 4 games, 19 plus 4 is 23. 5 games, 27. And 6 games is 31. So there's my table of values for Galaxy and for Less. So I've created my table of values based on my equations. Okay? All right, so let's take a look at graphing this now. So anytime I'm graphing, I need to make sure that I have my X axis labeled. So this is the number of videos rented or video games rented. I have the total cost. That's my Y. So the number of video games along the bottom, the total costs along the side. I also want to give my graph a title. So I'm going to call this video game rentals. And I'm going to use my table of values this time to come up with my points. So I could have done I could have graphed this using y equals mx plus b, where if I was looking at the equation of a straight line, this 4 would be my m, and the 7 would be my b. I could graph it like that, but I'm going to graph it because I used a table of values. I'm going to graph it using a table of values. So there's a few different ways that you can graph, so I wanted to show you this way as well, just to make sure that you had this as well. So I'm going to use my green for Galaxy. Remember, it was 0 and 10, so that was my first point. Then I had 1 and 13, 2 and 16, 3 and 19. Then I had 4 and 22, and I ran out of room. So I'm just going to go ahead and connect these points right here using a straight line, and I'm going to call this G for Galaxy. Now I'm going to use plot my points for less video game. So again, I'm going to use my table of values. It was 0 and 7, 1 and 11, 2 and 15. Oh, I skipped one. Let's go back and fix that. So 1 and 11, 2 and 15. Then we had 3 and 19. Look, there's our point of intersection. And then we had 4 and 23, so right there. Again, I'm going to connect these using a straight line. If you're drawing this on a piece of paper, your line is going to be much straighter than mine. If you're using a ruler, and I'm going to call this 4 less. So the red line is my 4 less, the green line is my Galaxy. So where's my point of intersection? My point of intersection is right here. It has a coordinate of 3 and 19. So what does this represent? Well, this represents when I rent 3 games, the cost will be $19. And it's going to be $19 at both stores. So when will the total rental cost be the same for both stores? When you rent 3 games. So we weren't asked to explain anything else from this question, but you could say, well, if I'm renting less than 3 games, then I maybe want to rent from 4 less because it's cheaper. If I rent more than 4 games or 3 games, then I want to rent from Galaxy because that will be cheaper. So once we can see visually where our point of intersection is, depending on how many games, if we always rent 3, then it doesn't matter. We can go from to whatever store, whatever one's closest. But if we're renting less, then go for 4 less. If we're renting more than 3, we're going to go with Galaxy because we want to maximize the amount of games we can rent for our money. Let's do one more example. So here we have, again, 2 situations. Paris Fitness Club charges a flat fee of $25 per month plus $5 per visit. Panthers Fitness charges a flat fee of $35 per month plus $3 per visit. For how many visits per month is the total cost the same for both clubs? Well, there are 2 things that we need to look at. We need to look at how many visits we're making a month and how much the cost is going to be. So those are going to be my two variables. So let C represent total cost. And let's let V represent the number of visits. So let's use this information to come up with two different equations. So I'm going to use green for Paris. Actually, let's use red for Paris. So the total cost, C, is going to equal $25 per month plus $5 per visit. For Panthers, let's use black. We'll do the total cost is equal to $35 a month, but the number per visit is only $3. So those are the two equations that I'm going to use. So instead of creating a table of values, let's graph this now using our equations. So remember, our equation of a line is y equals mx plus b. So our 5 and our 3 will represent our slope, and our 25 and 35 will represent our b. Okay, so the m is the number in front of our variable, and the b is the number all by itself. Okay, so for Paris Fitness Club, I'm going to use the red, so PFC. My slope is 5, or 5 over 1. Remember, this means I go up 5 and to the right 1. And my y-intercept is 25. So let's go ahead and plot that. So I have to look at my scale. So my x is going to be the number of visits. And my y is going to be my cost. Okay. My x goes up by 1, so 0, 1, 2, 3, 4. My y goes up by 5, so I have to take that into consideration. So I'm going to start by plotting my y-intercept at 25. From here, I need to go up 5, but that's only one line in my graph, and then over 1. So up 5 over 1 is right there. And I'm going to keep following that pattern until I run out of room on my grid. And then I'm going to connect these using a straight line. So this is PFC, Paris Fitness Club. For the next one, I have the Panthers Club. My slope is 3, or 3 over 1. So that means I go up 3 units and I go to the right 1 unit. And my y-intercept is 35. So I can go ahead and plot my y-intercept, but I'm going to come up with some difficulties when I'm trying to plot my slope because my scale goes up by 5, and so I would have to do some pretty good guessing to determine where my exact points will be. So one way to get around this is if I'm looking at my scale, I want to try to get my slope. So remember when we talked about equivalent fractions? This is going to come into play here. I want to write a slope so that it's going to be a multiple of 5. So I can do that by taking my slope and multiplying it by a constant. So because I want a multiple of 5, because that's what I'm going up by, why don't we go ahead and multiply both our numerator and our denominator by 5 to get a new slope that's going to be equivalent to 3 over 1. So 3 times 5 is 15, and 1 times 5 is 5. So this means that I go up 15 units and to the right 5. So when I'm looking for my other points, that's what I'm going to do. So that's a good hack to do. So remember, I'm going up by 5, so 5, 10, 15. But for every 15 units I go up, I have to go over 5. So 1, 2, 3, 4, 5. There's my point of intersection right there. Let's just plot another point. So I'm going up 15, so 5, 10, 15, and I'm going to the right 5. 1, 2, 3, 4, 5. There's my next point. Let's go ahead and plot and connect those using a straight line. So there's Panthers Club. So now that I have those two lines graphed, I can identify my point of intersection. So my point of intersection looks to be the point 5 and 50. So what does that mean? So my point of intersection is 5, 50. That's the coordinate of the point where they cross. And what does that mean? So if I go to the gym 5 times a month, the cost will be $50 for each facility. So if I was going less than 5 times a month, maybe I would go with the Paris Fitness Club. If I was going more than 5 times a month, I would end up going with the Panther Club. So that's how we can use this information, our point of intersection, to interpret the graph based on real world situations. If you have any questions about this lesson, please reach out to me, send me an email, or sign up for a virtual help session, and I will see you in the next lesson.